Okay, good. So the real problem for me was I wasn't sure what to talk about. This was the title I was given. And there's a lot of material that can be covered by that. I thought I'd start off with a little bit of history. In the early 1960s, Viktor Safronov started looking in detail at the kind of processes that you have to think about to make planets. And one of the things he wanted to calculate was how long does it take to build a planet. So here is the kind of calculation he did. Think of a disk with gas and planetesimals. One of the planetesimals is the biggest one, M1, and they're all going to grow by collisions. So I want to follow the biggest one and see how long it takes for it to become what will eventually be the planet. So the first thing to do is to calculate the cross-section. The cross-section is the geometrical cross-section, but enhanced by gravity. And so if you have a planetesimal coming by here, moving with a relative velocity v0, and you say, well, as long as it can somehow hit this planet, even at the very edge, it'll be captured. What is the value of this b? So if you look at conservation of angular momentum, conservation of energy, it's very easy to derive the fact that the cross-section, pi b squared, is the geometric cross-section times this gravitational enhancement factor. And what this is really the escape velocity from m1 squared. So that's a measure of the gravitational attraction. And you compare that with the random velocity of the planetesimals. And so that tells you how well this thing captures. And this parameter here is actually twice the Safronov parameter, which unfortunately people don't seem to use that name anymore. It sort of died out in the 1990s, I think. Anyway, if you have this, you can think of a cylinder in time dt. You cross through a cylinder which has this cross-section and a length v0 dt. And you can ask how much mass is in there, and then you get this equation for the m1 dt. It's the density of material in the background, the velocity, and this cross-section. And then you can integrate that and ask how much time does it take to build up a planet. Of course, you have to take into account the fact that rho decreases with time as you eat up more and more planetesimals, the background density decreases. Here's a solution. You can actually do it analytically. If you define z as the ratio of the radius of the planet at time t to the final radius, then the time it takes to grow to size z is given by this expression. There's this very nasty term here, which is basically linear until z gets very, very close to 1, and then this kicks in and it shoots up. But for z equal 0.99, which is good enough, it has a value of about 3.5. So it's a few. And the real time is in this constant tau 0, which is given by the mass of the planet, its density squared, some numbers, all this to the 1/3 power. That's not a very important part. But it goes like the period, which makes sense because the longer it takes for the planet to complete one circle around the sun, the longer it takes to gather up the material. It depends on the surface density of material. The more you have, the less time you can build a planet. And it involves this cross-section. Okay, so what do you choose for theta? Well, Safronov argued that the random velocity must be due to gravitational interactions between the planetesimals. They're stirring each other. And so you would expect that the random velocity would be somehow roughly the escape velocity from the biggest particle, say, which is not much bigger than anything else. And so theta ought to be around 1. If you plug it in, here are the numbers you get for tau 0. So the Earth you can do in about 5 million years, which doesn't seem like a terrible thing. Saturn takes over 1 billion years. And Neptune, Uranus and Neptune, you can't make in the lifetime of the solar system. That's a problem. Okay, so how do you deal with that? Well, if you increase theta to 5, say, that gives you a factor of a few. But again, Neptune is still taking longer than the age of the solar system to build. Well, it turns out that when people did numerical models of many body problems, Greenberg and colleagues in '78, Weatherall and Stewart, they found an interesting thing. What happens is if you start off with a density distribution of planetesimals, a number of bodies, function of mass here, you start off with something like this at T0, they collide and they grow, and what you find is that after a certain amount of time you have one really big guy that's running away from the rest of the distribution. Runaway growth. And a simple way to look at it is if I write down the same equation that Safronov wrote, but I look at the rate of growth of the largest particle compared to the next largest particle. That's, well, m is just r squared, is just proportional to r cubed, so that's just r squared dr1, dr2 squared dr2. And then here, if I neglect the 1, I just look at the Safronov parameters, I get this. This gives you a differential equation, which is easy to integrate. You get this. And what this tells you is that as R1 grows, the ratio between the biggest body and the next biggest body grows. One of the biggest body just starts running away. And what this means is that when you're doing this calculation, you're looking at the ratio of the random velocity to the escape velocity from the largest body. But the random velocity is due to stirring. If the largest body is much, much bigger than all the rest, it doesn't get to stir very much. Whatever it stirs, but most of the stirring, most of the random velocity is due to stirring by the much smaller guys. In that case, the escape velocity from the largest body is going to be much larger than the random velocity. This gravitational factor will be much larger, and that helps a lot. And what you get is, if I take, for example, theta equals 1,000, well then things become at least more reasonable. And so you can make Jupiter in a few 100,000 years, and even Neptune can be made in tens of millions of years. That looks a lot better. That's the first part of the solution. Second part of the solution is that you don't accrete the whole planet as particles. You draw in gas from the outside as well. There are two processes. And so all you need to do is really build up the core, and then somehow if you could magically add the gas, you would save a lot of time. Speaking of time, okay. So let me just point out that this is not the only solution. Maybe you don't build planets like this at all. And so I found an early paper of Kuiper's, 1951 actually, where he says the formation of the planetary system was a special case of the very general process of binary formation. You make planets like you make stars. That's another alternative that has to be considered. There are reasons why people don't consider it so much. It's kind of hard to do, but it's something that you should bear in mind, and I don't know if anybody's going to talk about it. I don't think I'll have the time to, but let me show you the rest of this accretion story. So how do I add in the atmosphere? Well, Dave told us very nicely about it before lunch. Here's an early calculation by Perry and Cameron where they did it using an adiabatic atmosphere. And what you see here are several things that Dave talked about. This A parameter is really distance from the sun. And the solutions are not very different for different distances from the sun. It's not very sensitive. Here you have the total mass of the body, and here you have the core mass. And you can see that for core masses of, like, say, 60 Earth masses, you're getting something like 50, 60 Earth masses total. You have a small atmosphere. As the core mass increases, it influences the gas around it. And this goes up, and then eventually it turns over. And then the argument was, this is a critical core mass. Once you get to 120 Earth masses, the atmosphere collapses. That's a really big number, yes?
About the runaway growth. So you say it is the biggest body that does most of the stirring.
No. The biggest body is the one who's growing. But the smaller bodies do the stirring. So the planetesimals move slowly, and the biggest body can grab them in.
Okay, so the V0 does not grow with time.
That's right. Yeah, V0 grows, but it grows more slowly than okay? Okay. All right. This assumes an adiabatic envelope. And as Dave pointed out, he did all the work for me, what you really need to do is look at a radiative envelope. And so here is a calculation by Mitsuno, 1980, which shows the same kind of solution, but now the critical core mass is something like 10 Earth masses. That's a lot more reasonable, and that's the kind of number you see. What I find particularly interesting is this solid curve is the exact solution of Mitsuno. The dash dot curve is the simple model that Dave described. The fit is really remarkable. So the simple model, the real proof that the simple model is a good one is that it fits very well to what you get when you do complicated things. Okay, so here's just a quick review of what Dave just told us. You have the equation of hydrostatic equilibrium. You have the equation telling you what the thermal gradient is. That gives you a relationship between temperature and pressure. You add in an ideal gas equation of state, and then that gives you rho as a function of R. It depends on the opacity, it depends on the luminosity, and the luminosity you get from the m dot core, the rate of growth of the core. And so you can plug all that in and you get rho as a function of R. If you do the integral to calculate how much mass you have in the envelope, and then you say that the total mass is equal to the mass of the core plus the mass of the envelope, this is what it comes out to. I've put together all the constants in here and left the important variables for you to see. So here's, okay, so this is what Dave described, and this is a very close approximation to what you need. When this turns over, then you get the critical core mass. And as I showed you, it's about 10 Earth masses. Here's a calculation that actually did all the physics. And again, this is something that Dave showed you, but I'll do it in a little bit more detail. This solid line is the growth of the core. So right in the beginning, you start accreting planetesimals. It grows very, very quickly. You eat up all the planetesimals that there are in your region, and then sort of things stay pretty constant for a while. In the meantime, you start adding gas. And you add gas very, very slowly, slowly. The total mass of the planet grows. Eventually, around the point where the mass of the atmosphere is equal to the mass of the core, you get sort of a runaway, things just take off, and you build Jupiter. That was the story. One thing that's worth asking is, if this is the critical core mass, why doesn't the gas just fall on? And Dave explained part of it. You have to release energy, but I think one part that he didn't stress is that the luminosity here is extremely high. When you do the calculation using that equation, and the luminosity that you get here, this is growing extremely quickly. The luminosity is high, and this is not the critical core mass. This becomes the critical core mass after everything is cooled off. And so that's another way of looking at what you described. Okay, so this is it. We're done. How long does it take? It takes about 8 million years. That sounds fine. Saturn takes off a little bit more slowly. This is the surface density in the background of solids, so it takes a little bit longer to build up. But okay, less than 10 million years. Uranus takes a little bit longer. But maybe things sort of stopped here, and this would sort of look like Uranus, a core up to here and a little bit of atmosphere. So if you get rid of the surrounding gas, how much time do you have? Have we solved the timescale problem? The answer is I don't think so. This is a version of a graph you've probably seen earlier in the conference. You're looking at various groups of stars and how many of those young stars have disks around them. And so you can see that this is the age in millions of years and percentage. So you can see that young stars, most of them have disks, and it very quickly goes down to around 0 at 5 million years. So I would like to say that you have about 5 million years to do all this. Jupiter, 8 million, 5 million, we won't quibble, but the rest are kind of difficult. So how can you reduce this time? Well, if you look at this equation again, you see that one way of reducing the critical core mass, having this collapse occur earlier, is to reduce the opacity. Here's what happens if you have an opacity of 10 to the minus 3. Here's 10 to the minus 4. If you could somehow do that, you would really gain and speed things up. Okay, so let's look at what happens. If I have a mass of grains, and this is their density, then the number of grains, and this is the radius, this is the number of grains that you get. Extinction depends on the total surface area, so I multiply that by pi a squared, and here's the extinction, the optical depth of that mass of grains. But then again, as Dave pointed out, that's not really the whole story. The cross-section of a grain is this geometric cross-section times some sort of efficiency factor that really depends on the ratio of the grain size to the wavelength of light you're considering. Here's an example. It's this factor, 2 pi a over lambda, is the circumference of the grain divided by the wavelength. Here's what happens. When the grain is much larger than the wavelength, and there are three sort of efficiency factors that people talk about. There's the efficiency for scattering, efficiency for absorption, and the sum of the two, which is the efficiency for extinction altogether. Okay, so you see that for this particular case, it depends on the material that the grain is made out of, and for typical materials, this is sort of the absorption cross-section, and the red and the scattering Q. And you can see that they're about 1 each. So, okay, that's fine. But the minute you start getting to small grains, to cases where the grain is significantly smaller than the wavelength of light, these things go down. The scattering goes way down. The grains become black. They tend to absorb rather than scatter. And the absorption also goes down linearly with the grain size. So, really what you have to do is add this Q extinction, and Q extinction for small grains is roughly like A. So, if the grains are sufficiently small, the optical depth becomes independent of grain size, which is an interesting result. How many grains do you have? Well, if you think of this gas that's coming in from outside and carrying grains with it, think of a given mass flux, then here's the flux. It's the number of grains times the mass of the grain times its sedimentation speed. It's sitting in the atmosphere and it's sort of sedimenting out. Okay, large Knudsen number, that means that the grains are small and the gas is dilute. Then you can write down a formula for the sedimentation speed. It's this. G is the gravitational acceleration. This is the thermal velocity of the gas molecules, and then it depends on the amount of gas you have and the density of the dust and the dust size. And then I can say, okay, how many grains do I have as a function of flux? And then it's just this. And you see that it depends on 1 over a to the 4th.
Does the second
Yeah.
one come from the Stokes equation or
This?
Epstein?
The Epstein equation, that's right. That's right, Epstein drag. And it's going to be a little bit different if I use Stokes drag. Okay, therefore, the optical depth can be tied to the flux. If I know the number of grains and I know the cross-section and so on, if I have some region L and I want to know what's the optical depth of the grains in that region, given the flux and assuming a steady state, I can get the optical depth. And again, for small grains, Q extinction is A. For larger grains, it's a constant. Okay, then you can do something interesting. You can say, well, I've got these grains sitting here. What are they going to do? Are they going to grow? They could move around, Brownian motion, or bigger grains overtaking smaller grains, growing, and then they'll fall out. And so I can ask, what are the timescales for growing, for example, and for sedimenting? The timescale for sedimenting is just the time to get through this layer L. And putting in all the stuff that I put in, you get this value. The timescale for coagulation is the mean free path between grains divided by the thermal Brownian speed of the grains. So you assume that they're all the same size, for example, and they bump into each other and stick. How long does that take? Well, that's this formula. And then you say, well, if the grains are really big, they're going to fall out before they get a chance to grow. If they're really small, they'll just sit there and grow. What's going to determine the size of the grain when these two are roughly equal? Okay, so I set that equal to 1, and that gives me a grain size. And then maybe I can use that to calculate the optical depth of the layer and get some idea of what should be going on. This is a way to deal with this dirty problem that Dave mentioned of what do you do about opacities? And this is just the grain opacity, but gas opacities are much easier to deal with. Okay. So here's the optical depth that you get from doing this whole calculation. It's roughly linear. It's the dust density to the 10/9. It depends on what the flux is, how much dust you want to be pushing through that region of the atmosphere and the size of the atmosphere and so on. And some of the things are not very important, like the temperature and the gas density. Okay, so that's that. So you can calculate the grain size using an argument like this. You can calculate the opacity, and you can begin to try to solve this problem of what really is the luminosity. We did this for those Jupiter models that I showed you. So here's an early Jupiter model. This is the radius in centimeters. Here's the grain radius that comes out of such a calculation. Here's the optical depth. You can see the optical depth is really very low in this whole outer region. And at some point, of course, the temperature gets high enough that the grains evaporate, and so this whole thing is irrelevant. And this is sort of where that happens in the particular model we were looking at. And then when you do all that, that's the simple model. If you do it in a more complicated way, you actually put in a real equation for the growth of the grains and so on. You get a rather complex distribution of, here's the height in the atmosphere, in the upper atmosphere. This is the grain size, and the colors tell you something about the number of grains. And so you can see that you get the grain size distribution evolves. There's lots of small grains way up high, and as you go deeper in, they grow, and you have fewer grains like this. And it's a complex calculation. I don't have time to describe in very much detail unless there are questions, but that's the paper describing it. When you take all that and you put it into a real model of Jupiter, you find that you can shorten the time extremely, to a great extent. From 8 million years, this is the same model that took 8 million years earlier, you're getting in under 1 million years. So, yeah.
Are you imagining just material falling onto the planet, and as it falls in, at some point it condenses and forms grain?
That's an excellent question, and the guess is not quite right. I'm assuming that the gas is coming in, falling, this part of the calculation, the gas coming in, and it's carrying grains. And in the original calculation, they assumed what's called the Podolak opacities, which was about 1 for, under these conditions. I mean, it's a temperature-dependent opacity, but in the outer regions where it's very important, it was about 1. It turns out that it's much less, and so the gas can just fall in more quickly. But we assumed this calculation was done for the grains coming in with the gas.
Okay. And my second question is, I don't have an intuition about that. How do you form those grains to begin with?
They're sitting there in the nebula. Okay?
Is it okay to assume,
Yeah.
is it okay to assume that all the optical depth comes from the grain, not the molecules?
No, it's both. It's both.
But I don't see you put that.
I didn't take that into account because the grains are the major contribution in this particular temperature range. Okay?
Which temperature range?
100, 200 degrees, 300 degrees in the outer atmosphere. The temperature at the edge of this envelope is like 120, 150 Kelvin. Yeah.
Are you assuming for the grain sizes that are coming in? So we know why some opacities don't match just for accretion.
Yeah, okay, so that's why I said Podolak opacities, whatever Podolak assumed.
You're using that for this.
Yeah, this calculation, and it says Movshovitz et al., but Podolak is the father of the calculation. Okay? Any other questions? Yeah.
Maybe it's a trivial question, but how is the final planet mass determined?
That's a good question. Not from here. The idea here is, okay, well, it's going to go up and we can go home now. But I'll show you in a second how the final planet mass is determined. Yeah. We assume that it was. We assume that it was. When it becomes a problem when you have convection, and that's a complicated issue. It depends on the relative size of the grains and so on. I've started looking at grains that can break up also, and then it turns out the results are different. Yeah. It's a dirty problem. Okay? Okay. Anyway, the point is that what took 8 million years previously now takes maybe 800,000 years. You've gained a factor of 10. So what's nice about it is you can say, well, I assumed that the background density of solids was 10 grams per square centimeter. Maybe I can get away with less. And it turns out you can. 6 grams per square centimeter still gets you in well under the 5 million years. 4 grams per cc brings you up to the, per square centimeter brings you about up to the limit. But you see you can make different kinds of planets. And again, this illustrates the point that Dave had shown, that the critical core mass can vary depending on how much time you allow yourself to do this. So all that actually, not only was the simple model correct, it's borne out by detailed calculations. Yes?
They mentioned 1 gram per square centimeter is kind of that's the reference value usually, right?
No, that was for the opacity. This is surface density. Okay.
I have the English units.
Okay. Continue?
Sorry,
I
thought
yeah.
Dave's results, you were only logarithmically sensitive to the disk, so you weren't really sensitive to the surface density in the nebula.
No. That was, okay, that's a good point.
Yeah.
That's a good point. No, you are, there's two things. There's the distance from the sun, which is not a very important factor. That sort of fixes the Hill sphere radius. And that's not important. But how much material you have is very important.
That is important.
Doesn't the distance from the sun change your temperature and hence your opacity?
Yeah, not very much. Okay.
And also,
Yeah.
in both Dave's talk and your lecture, you're always assuming it's thermal equilibrium. That means the luminosity is equal to the GMOR times the accretion rate. But is it always true, like if you compare the thermal timescale of the atmosphere and the accretion timescale of the atmosphere, will you always find that the accretion timescale is much longer than the timescale for the atmosphere to settle down onto a thermal equilibrium state?
I think that's true. Yeah. Yeah. All these models are not dynamic. They're quasi-steady state. In other words, you calculate a model assuming steady state. You calculate the luminosity and the temperature structure and everything, and then you go ahead and you change the core mass a bit and you redo it, and that's where you get these gaseous atmospheres.
Yeah, I know how it's calculated.
Okay.
I'm just asking the assumption that
I think
it's
that
always in thermal equilibrium, whether it's
always, I don't know, maybe you could think of regimes where it's not the case, but I think in this particular case, I think that's certainly true. Okay, I'll skip this one. Now, you asked about the gas coming in. There's a subtlety there. I mean, once it goes up to infinity, you say, okay, I can get what I want and I'm done. But it's not true. And this is just to indicate that you've got to worry about how the gas streams onto the planet, and it's not simple. Here's what a more detailed calculation looks like. In fact, you do get the gas going up very quickly, but if you play correctly with the parameters, you can get it to sort of level off just at 318 Earth masses. But you got to fine tune it. You pick there's certain free parameters, and you pick them.
So what stops the gas from creeping down?
You open up a gap. Okay. Anyway, there's another thing that can actually help you speed things up, and that is the mean molecular weight of the envelope. This is a solar envelope, and this is one that's enhanced 10 times solar. So you don't need much. And then the question is, what happens with all these planetesimals that are coming in and depositing material in the envelope? What happens to that? So, we looked at that a while ago, and the result at the time was that, okay, this is the idea. Planetesimals come in, they heat up, passing through the gas, they vaporize. The vapor gets deposited where it gets deposited. Then you look at the vapor pressure. Will that vapor be supersaturated or not? If it's supersaturated, some of the stuff condenses and falls to lower levels. And you just keep letting it fall until it revaporizes. And so you can do this calculation. This is just to give you a feeling for the atmosphere. We did this as the atmosphere grows, function of history. So this is the atmosphere at 18,000 years. This is after 2.4 million years. This shows you the temperature. So the temperature at the beginning is not very high at the center. It's about 1,000 Kelvin. Later on it gets up to 10,000 Kelvin. You can keep a lot of stuff gaseous at those temperatures.
Can I ask?
Yeah.
Just to clarify, so the models are purely radiative or radiative and convective?
Radiative convective. They're models that came from an earlier calculation by Podolak and Bodenheimer and company. And we just used it. They're not self-consistent. We just used that as the background temperature. Okay, so just to get a feeling for what happens, this is what happens to rock. This is the hydrogen-helium pressure. This is the partial pressure of rock that gets deposited and turned into vapor. This is the vapor pressure of rock. So you're not allowed to be above this curve and be gaseous. And if you just look for a second here, I mean, there's tens and tens of orders of magnitude difference. All of this stuff gets heated up, vaporized, put in the atmosphere, but then it freezes immediately, condenses, and just falls down, and it'll have to fall to somewhere near the core. So rock gets deposited in the upper atmosphere, but doesn't stay there. Yes?
Do you do chemical calculations inside the atmosphere? So basically, if input one material, for instance, some kind of ice or rock, gets into the atmosphere, vaporizes, you might reassemble in completely different chemical composition.
That's for the next student to do. Eyal didn't do that. No, we just left it as is.
What's the time scale for settling of the rock from up in the atmosphere to the...
What's the size of the grains that you want me to assume?
Oh, yeah.
Okay. So no. This is it's a legitimate question. I'll try to say something more about it at the very end of the talk. But this is all we did. I mean, this was a master's student, and I couldn't make him work too hard. Okay. Here's the same thing for ice. You see, here's the hydrogen helium. Here is the ice that you put in. And this is the vapor pressure of water. So what this is telling you is that all the ice that you put in as vapor can stay there. It's no problem. So the ice stays in the envelope. We looked at some sort of organics. Never mind that. I don't know what the organics are. So, you know, you can, we took, I just looked up the heaviest organic in the chemical, the CRC tables, and just to see, yeah. Excellent question. Give me 2 slides. Okay. Okay, so nearly all the rock goes into the core. A little bit stays just above, quote unquote, the core in a very warm region. Same thing for the organics. They can take up a little bit more space, but the water stays in the envelope. So I can raise the mean molecular weight of the envelope, and this may be another way of shortening the time for forming a planet. We didn't carry it any further than that. Now, here is work in progress, and yeah, just right. And Ravit and Peter Bodenheimer and Eric Rosenberg and Michael Lasovsky is here, and me. Work in progress in red. In other words, don't tie me down to this. But now the question is, do the same calculation, but allow things to mix. Mix back up. What's going to happen? So if you have a small blob of gas and you give it a sort of a flick up, it's going to expand. The temperature inside the gas is going to be adiabatic. The temperature outside is going to be whatever it wants to be based on the state of the planet. So you have to look. If this is warmer than the surroundings, it'll continue to go up and it'll be stable against, it'll be unstable against convection. Convection will occur. And so this is, since dt is negative, right, so you want this to be less negative than that. And I think I got that right. Anyway, that's the standard criterion for convection. If you have a mean molecular weight gradient as well, not only does this have to be hotter than the surroundings, it has to be hotter enough so that the material here, which has a smaller molecular weight, has a larger molecular weight than the material in the surroundings, will still float. So it makes it that much harder. And this is called the Ledoux criterion. A little bit more complicated. But we did that. And so we redid the whole calculation. And here, for example, is one case. These are not the same, these are improved atmospheric models that Peter Bodenheimer sent us. We're talking here about a 1 kilometer planetesimal, and the background surface density is 10 grams per square centimeter. And you ask, okay, these 1 kilometer planetesimals, a lot of them vaporize at the edge of the planet. Some of them go all the way to the core. This is the material that you deposit. This is the Z of the material that you deposit, the average Z as a function of radius from the planet. And then you say, okay, now let me apply that criterion. I know what the temperature is everywhere here because Peter Bodenheimer told me. I know what Z is everywhere, what mean molecular weight is. What does mixing do? And it turns out mixing does this. It takes all of this material and mixes it up to here, and it takes this material and mixes it down to there, and here you got a slight radiative zone where mixing doesn't occur. And this is the new setup for the material. This is where it wants to be. And then you say, but I've got this restriction of vapor pressure. I've got to make sure that the partial pressure of the material here is less than the vapor pressure, otherwise it won't stay vapor. So water, this is the vapor pressure of water. No problem. If it's water, everything stays. If it's rock, it does that. So everything up to here can mix, but this part becomes grains. It recondenses out. What happens to those grains? Do they grow? Do they fall? Can they be kept floating by convective currents? We don't know yet. It's work in progress. But that will tell us something about the opacities. Let me show you another example. This is for 1 kilometer planetesimals. If you have 100 kilometer planetesimals, you don't have that big peak here. They plow in and deposit most of the mass inside, and then you can do the exact same calculation. You mix it. Now there's no problem. It all gets mixed, most of it anyway. And then water has no problem. Everything that gets mixed can stay there. Rock doesn't like these low temperatures, and so everything here would condense out if it were rock. Finally, if I go to a case where the surface density is only 6 grams per square centimeter, then everything occurs more slowly, and the temperatures in the envelope are lower. And here, again, this is the stuff that gets deposited. This is what mixing does. But now, because the temperatures are lower, even this outside layer has to condense, and so you would get a water or ice cloud up on top. And if you do it with rock, that's what happens. And I will stop here anyway, so questions?
Okay, good. We have 5 minutes for questions. Yes.
The question is, what is the motivation of studying those dust grains coming together with the gas? Are you hoping that the accretion of those dust grains could contribute a lot to the core mass?
No. I think, first of all, to answer your question, I just want to know what the physics tells us. And so you want to put in all the physics. But what I'm thinking here is, in this region, you're going to have a lot of grains. That will affect the opacity. That's going to affect the whole evolution of the planet. And so really that's the issue. And then, and here, of course, so I've got the opacity, and I've got the mean molecular weight here, and so what wins? Does it improve the time scale or not?
Yes.
You say it will affect the occlusional plan, but then you show at the same time it's convective. So how would the transfer of the brain affect the
Okay, right. If it's convective, then the opacity wouldn't make much difference. You're right. But there's got to be a radiative zone somewhere at the end here, and that's really what you're interested in.
For posterity.
So I want to make a few comments. So first of all, for the last questions, it's also interesting, this calculation, because it will tell us if there is a homogeneous distribution in terms of the different heavy elements. So what Maurice was saying is that, for example, the rocks will tend to go deeper to the center, while maybe the water will stay higher up. And that's important because it can tell us something about the structure that we should expect. Another point maybe to make is that, you know, this mixing calculation does not take into account the effect of the high Z material on the equation of state, and therefore the evolution and the growth of the planet. So things may change as we are going to do it more correctly. And the last point is that if we get planets or protoplanets with this gradual distribution of heavy elements, it can be that we do get regions that are not convective, and that's very important for the evolution and the temperature profile of planets in general. So that's another motivation for this calculation.
Other comments, questions?
So in the process of coagulation, do you take into account the heat that's generated in the process?
No.
I see. Is it considerable?
I never calculated it, but my gut feeling is that it's not. But it's an interesting exercise to do. I think it's very small.
Okay, thank you.
It's not a chemical bond. It's not a chemical bond in the sense of, you know, forming a molecule. It's just a very simple change in surface tension and stuff like that.
Any other questions? Yes. Last question.
So my intuition is based on Earth's atmosphere, where you need pre-existing nuclei to actually condense anything onto. Now you're saying that here you seem to have enough grains from the interstellar medium, but is it very sensitive to the assumptions that you make about those grains, their sizes or their density? And does it mean that you can't form giant planets in relatively clean parts of the galaxy where you don't have enough grains, or anything
I
like that?
wouldn't go that far. I mean, if you looked at the vapor, you're right that if the atmosphere is clean, then you have to have supersaturation of a high degree. But when you're talking about the atmosphere, a high degree is a factor of. You're talking about a factor of 10 to the 50. Yeah,
Okay, let's thank Morris again.
just get my thing
And
out
now
again.
we have Ravi Taleb, also from Tel-Aviv. Also about giant planets. And do you have the microphone on?
Oh, I do. Sorry. You're lucky I didn't walk off with a computer. Okay.
How do I change to this computer? We need technical help here. Okay. את יכולה להחליף לי את המחשב? Okay, I'll start anyway before the presentation, but it's not very easy to tell new things after these last two talks, but I'll do my best. So I was asked to talk about giant planet formation and internal structure, and these are typically two different topics, but as hopefully you are convinced by now, these are actually coupled. I mean, the formation process essentially determines the final structure of the planet. It's not working. What? Should I?
Let me see what happens. This sometimes works.
No, but I think you have to.
This is, so the problem is that this one's still connected.
Yeah, okay.
But where?
Maybe.
Is it this?
That's like.
This is the power. Here.
Oh, there it is.
What's that? No?
It's a USB port that'll connect to this.
Oh, I didn't, okay. So maybe you can.
You can plug it.